Swayam Prabha. Digital India. Educated India.
So, if you recall, in last two classes we have discussed couple of op-amp circuits, and the circuit elements that we have used, which are actually in the exterior of this op-amp, were resistors, right? For example, in case of inverting amplifier, we have discussed this circuit, inverting amplifier, right? So this is the input, right, which is applied to a resistor R1. This is the feedback resistor RF. It is connecting this input inverting terminal and this output terminal, right, of this op amp. This is the output. This is the non-inverting input of the op amp, and this is grounded, right? So you can see here we have used resistor. Here also at the input one resistor. In the feedback loop also we have used another resistor, right? This is the case of inverting amplifier. Similarly, in case of non-inverting amplifier, we have used this circuit. Here the input has been applied to this non-inverting terminal, right? So this is that input, isn't it? And we have a feedback, negative feedback, same as like this, right? We have this feedback resistor RF connected between this output and the inverting in terminal of this op amp, and also we have a resistor which is which was R1, and this resistor was ground, isn't it? So here also you can clearly see that the feedback element is resistor. At the same time, here this another component is also resistor, right? So now think what will happen if we do not use these resistors, but rather we use some other circuit components or the electronic components. Okay, then what will be the relation between this input and output? Using these resistors, we have already derived what is the relation between this input and output, what is the gain of these amplifiers, right? And let us now use some other electronic circuit components as well and try to estimate the gain as well as the relation between the output and input, right? So for that, let us go to the next page and let us start our discussion on a different circuit which is known as this integrator, which is known as this integrator. So how does this integrator look like? So it is quite similar to that of this inverting amplifier, but only one difference is in terms of construction is that in the feedback loop, instead of this capacitor, instead of the resistor RF, now we have a capacitor C. This is say R1. This is same as this input earlier, and this is been grounded. Okay, so let us now see what is the relation between this output, or how can we express this V output in terms of this V input. Here also you can see this op amp is now operating in a closed loop because there it is output is connected with the input inverting terminal. So it is operating in the closed loop, right? As this op amp is operating in this closed loop, so the virtual ground concept is valid. So as this is at zero potential, so this will also be at zero potential, right? As we have discussed for our inverting as well as non-inverting in amplifier, right? Now let us say that one current which is flowing through this R1 is I, right? Then if we express this current I in terms of this Vi and R1, then we can write this current I is nothing but Vi by R1, isn't it, right? Okay, now we know no current can go inside or out of this op-amp input terminal, so no current here, right? So this I same current has to flow through this capacitor, isn't it? So if the current is flowing through this capacitor, right, then what will be the voltage develop across this capacitor? Then voltage develop across this capacitor, if the current flowing through is, if this is V, then we already know that this relation between this input and the voltage input current and the voltage developed across the capacitor can be written as this I equal to C into dV dt, right? Okay, this V is the voltage developed across the capacitor. So what is this? For this particular case, see, this is 0, right? This side is 0, this side is V naught. So it will be C into this of 0 minus V naught, right? So that way we can write it as minus C into dV out by dt, right? Now as these two are the same current, right, both sides you can see here I, so then we can equate these two terms, right? Okay, now if we equate these two terms, let us write it here in this, we have some space here. So Vi by R1 is equal to minus C dV out by dt, dV naught by dt, right? Then we would like to express V out in terms of Vi, right? Then obviously, then to take V out, we have to take an integral, right? Take an integration. So this V out, can be expressed. It will be minus 1 by R1. The C will come here, right? R1C, this integration of this Vi, then dt, isn't it? If you take the integration. So this is valid when this capacitor C was initially discharged. That means no voltage was there across this capacitor at time t equal to 0. Right. But if this capacitor was suppose initially charged by an voltage, suppose Vc, so maybe we can write it here, initial voltage across C, suppose this was equal to Vc. So in that case, this output voltage would be equal to, I think we have to do one, I think we have missed the negative sign here, right? Because if there was a negative, right? So this negative will be here, right? So V out will be equal to this Vc, because Vc we have assumed that capacitor was charged like Vc, so it is plus and this is minus. So it is Vc minus of this one, right? 1 by R1C integration of this Vi dt, isn't it? This is when if the capacitor, this is initially charged by an voltage Vc. Otherwise, this previous expression would be sufficient to relate the output voltage and the input voltage, right? Okay. So here, if you consider this equation, or if you consider this equation, so from these two equations, let me also underline this. From these two equations, it should be clear that this V out is proportional to this integral of this Vi of dt, that is the input voltage. So this is the reason why this circuit is called the integrator. Is it clear to you? Okay. Now, if you have understood this calculation, then tell me, suppose if we have applied Vi equal to 1 volt, okay, constant, okay, 1 volt. So if this input is 1 volt, then what will be the output voltage? Can you tell me? So what we are discussing now is that say the input is, this is 0, input is 1 volt, okay, and this is constant, right? This is the time axis. Then can you tell me what will be the output voltage or the waveform of this output voltage, this V out? So if this is your Vi, right? So definitely, right, you can do it easily. So it is 1 volt, so it will come out. So from this you can see the output voltage will be the a linear function, or basically a ramp function, right? It will be a ramp function, right? So it will be linear function of this time, right? So it will increase, right? So if we say like this is the output voltage that we are drawing, right, then this output voltage will increase linearly. But what will be the polarity? If we have applied here plus 1 volt here, then at this V output here, from here you can see there is a negative sign, right? And from also this circuit you can see it has been applied, Vi has been applied to this inverting terminal. So output is going to be the negative polarity. So it will be a linear function of this time, right? So this output will linearly a linear function of this time, because this is time, right? Okay, now tell me, can it increase like indefinitely? No, right? Because here we know that the output voltage cannot go beyond the either positive supply voltage or negative supply voltage. Here, as this output is this negative, so this V output or V naught cannot go beyond this V negative supply voltage, right? V negative supply voltage, isn't it? So this will be the maximum value after which the output voltage will saturate, right? Okay. And here, I think you have already noticed this part, that this slope, okay, the rising part or the linear part, that is dependent on this factor, right? This R1 into C, right? Now, if you change this factor, then obviously this slope, okay, this slope depends on what? This R1C, right? Right. So if you change this value of this R1 and C, then this slope is also going to change. Right? Is this clear to you? Okay. Then I have one more question to you. That is, suppose for the same circuit, integrator circuit, if we apply a sinusoidal input signal, right, like this. Okay, this is Vi. Huh? Okay, to the integrator. Then can you comment what will be the output voltage or output voltage waveform? V naught. This is time. Yes. So if this is sine, then obviously the output will be cosine, right? Because if you have to just integrate it, right, it will be cosine. So cosine function, you know that it will be like this, right? Maybe the drawing is not perfect, drawing it quickly, but you understand from here, right? It will be a cosine function, right? Okay. Then also tell me, if this input Vi is a square wave, okay, maybe I will take another color so that it would be visible. So suppose we have a square wave like this, okay, and we have applied this square wave at the input, right? Then tell me what would be the output voltage waveform. What would be the output voltage waveform? Exactly, it will be an triangular wave, right? Because see here, this is constant and it's positive, so the output is, this is suppose it 1 volt, suppose say this is plus 1, this is minus 1, this is minus 1 volt and this is 0, then for this we have in the last page only we have seen, right, it will be a linear function and slope will be negative, right? So let us say that till this part we get a negative slope like this, right? It is negative, so we get here a positive slope like this. After that again negative slope, right? Then we have a positive slope like this. So if this input is a square wave, the output of this integrator is going to be a triangular wave, right? Then can you comment what would be the magnitude here, or this highest magnitude here? Okay, see that, in the last page only we have seen here that this, okay, this slope, this depends on this R1C, right, this resistance and this capacitor. So similarly here also for this integrator, this slope will be dependent on this R and C. So this slope is dependent on the, this, as this slope is dependent on this R1 and C, so this value or the magnitude of this waveform is output waveform is dependent on the value of this resistance, capacitor, and also on the frequency, right? Because it also depends what is this time, right, time period t, right? Because if you have more time, then perhaps it will go and try to saturate, right? So it depends on these three things, right? Okay, now if we just reconsider the circuit, that simple integrator circuit that we have discussed in the last page, which was which was this circuit, right? This is C, this is R1, this is VI, and uh, this was ground, right? And this is that output V0, right? Now suppose this VI is a DC voltage, right? So for DC, this capacitor will behave as an what? This capacitor will behave in DC as an open circuit. So if this capacitor now behaves as an open circuit, then you can consider this op amp is now operated in the what? In the open loop. So this output voltage quickly saturates. It will go reach either plus V, V supply, V positive supply, or V negative supply, right? Output voltage depending on the value of this VI, right? And now suppose you are increasing the frequency. So as you are increasing the frequency, then what is happening to the impedance of this capacitor? That is decreasing, right? Because if you consider here this impedance is at like Z, and this is ZF, say, because this is a feedback ZF and this is R1, right? Then you can say like V output by V input, which is nothing but the gain of this amplifier, is equal to this minus of ZF by this R1. So what is this ZF for capacitor? It is omega into C, right? So omega C into R1. So what is this omega? Omega is, let us write R1C into omega is 2 pi F, right? So you can see for very low frequency, this gain, right? This gain of this amplifier is going to be very high. As you increase the frequency, not suppose it is not now DC, but if you are increasing, you are applying a sinusoidal signal, and if you keep on increase this frequency of this input signal, then the gain of this amplifier, what will happen to the gain? Yes, if you are increasing frequency, so the gain will now fall, right? So then if you plot the gain, maybe in dB, right, and if you plot versus this frequency, right, then you can expect one plot something like this, right? So gain is here dependent on this frequency, right? So and when the frequency is 0, means the DC, you have a your gain of the circuit will be very close to the open loop gain, which is very high, right? So that's how we have plotted it, this gain in dB, right? Now as you are increasing this frequency, obviously this frequency is in log scale, then the gain will fall down, right? And one more thing can also happen, that is these op amps, so far we have considered this as an ideal op amp, but in case of practical op amp you also have some offset voltage, right? So for lower frequencies, even if you have a quite high gain, okay, suppose in terms of some millivolt offset, due to the presence of some millivolt level of offset voltage, the output voltage can also now go to go into the saturation region, okay, for lower frequency, right? So to avoid that, what you can do is you can just add one resistor here, right? Suppose if you add this resistor RF in this feedback, so even if your input is in DC, so this the gain of this amplifier is now, so this is, you can consider it as an open circuit, and then the gain will become minus RF by R1. It is which is a finite quantity. So that will try to prevent the issue of the output voltage, this output voltage getting saturated, right? So is this clear, this integrator part? But remember again, this is a very basic type of integrator. The integrator which are generally used in actual circuit, they are a bit more complicated. Fine. Now suppose if you interchange this capacitor, the position of this capacitor and this resistor, interchange, okay, then the output, what you are getting here, that will be bit something interesting, okay. So this circuit, if it is behaving as an integrator, right, if you interchange the position of this capacitor and this resistor, then that circuit will behave as a differentiator. So let us see that in the next page. So op amp differentiator. Okay, so here as discussed, what we will do, we will interchange the position of this capacitor and the resistor. As this resistor is placed in the feedback loop, right, output to this input, so here we will give the name as RF, right? This is input, I, this is output. Fine. Okay, then again, if this current is I, right, we can consider the virtual ground concept, that is the ground. It's a closed loop condition, so this potential is also at 0, no current is flowing through this, so the same current I has to flow through this resistance RF, isn't it? So this current I can be written as this I equal to C dV dt, right? What is this V? Here V is nothing but this Vi minus 0, so basically it is Vi, so C into dVi by dt. What is this output voltage? This output voltage, you see, this is 0, so this output voltage is equal to minus I into R, right? and we know this I is this is the same I, so we can put the value of I in terms of this input voltage, right? So we can write CR dVi by dt, right? So here you can see the output voltage is proportional to the derivative of this input voltage. So that's why the name differentiator. Okay, here one thing you need to remember is that this differentiator circuit is more susceptible, okay, to noise compared to the integrator circuit, because this what we are doing the differentiation of this input voltage. So if there is any noise at this input voltage, so due to the presence of the noise at this output voltage, we will get an spike. Okay, because you know noise is what, if suppose some signal, okay, it is varying like this, okay, it is expected to be varying like this, but suppose due to noise you have an this type of small noise here like this, then when it pass to this output, due to the presence, you know, here the slope, this you can see there, this differentiator basically is gives you the slope. So compared to this slope, here the slope is very high, right? So at a result, maybe at the output, what you will get a very large spike, okay, due to the presence of this noise, right? So please remember that these differentiator circuit are more susceptible to noise compared to the integrator circuit that we have discussed just some time back. And the issue of getting a spike at this output voltage, that is here, due to the presence of this noise, that can be mitigated by placing one resistor in series with the capacitor before you apply, you know, now you apply the input voltage here, okay, like this, fine. So this differentiator part is clear to you? Okay, let us then here discuss another type of op-amp circuit where uh, we will use a diode at the output. Let us see how. So this is the op-amp, inverting terminal, non-inverting, output, right? This non-inverting, at this non-inverting terminal, we will apply the input voltage Vi. At this output here, we will connect one PN junction diode, okay, and we will have a negative feedback from this output to this input, right? So this op amp is now operating in a closed loop condition. So this is the output voltage, and we will connect one load resistance RL here, right? So the drop across this load resistance is the output voltage here, right? Okay, now let us see how this particular circuit of op amp will behave. So initially, let us say we have applied some positive voltage here. So when you have applied some positive voltage here, right? So this is the non-inverting terminal. So at this output, right? Here the output will be positive. As this output here of this op amp is positive, this will make this PN junction diode forward bias, right? So a forward PN junction diode can also be considered as a short circuit, right? So if you consider it as a short circuit, then you can see the output terminal of the op amp is now directly connected with the inverting terminal of the op amp. So basically then this circuit is nothing but an voltage follower circuit. You remember the voltage follower circuit that we have discussed last class, and where we have seen that for voltage follower circuit, output voltage will follow the input voltage. right? So that means whatever is the input voltage, that will go to the output voltage, isn't it? So that way what we can write is that when Vi is positive, V, if we say that this internal node voltage is V naught 1, V naught 1 is also positive, right? And then the feedback path is complete. It will behave as an voltage follower, right? When it is acting as a voltage follower, then the output voltage will be same as that of this input voltage, right? Fine. Now consider then, if now this Vi is less than 0, means if this Vi is negative, then what would happen? Yes, if this is now negative, maybe I will use some other color. So if this is negative, right, then this is non-inverting terminal, so this will be also negative. So if this is negative, this diode is off, means open circuit, right? If this diode is off or in open circuit, then you can see it is something like that, right? Means between these 2 points nothing is there, it is open, right? The circuit is broken. That way you can think of this closed loop is also broken, and this output is not connected with this output of the op amp is not connected with this RL now. Then this RL would become 0 in that case, right? So when this situation arises, right, then this is negative, V naught 1 is negative, right? In that condition, one negative current tries to flow through this diode, and which is not possible because the negative diode current is almost negligible, right? So then this output voltage is equal to 0, right? Then if you have understood this, these two parts, right, then think about it. If we have applied one sinusoidal signal at this input, right, then what do we expect at the output? What do we expect? See, here whatever is the input for the positive half cycle, the exact positive half replica we will get. Negative half output voltage is 0. Again for the positive half we will get this. Again for this positive half we will get this, right? So this is that time and this is that output. So basically all positive halves this circuit is passing, right, and the negative half this circuit is blocking, right? So it is nothing but in, from this you can see this is working as a half wave rectifier, right? So definitely its action is similar to that of an half wave rectifier circuit, right? So let us write it here that it is thing but a half wave rectifier, right? But in addition to this half wave rectifier, what we have seen is that if you consider one normal half wave rectifier circuit where you have applied in sinusoidal signal Vi, right, and this is the load resistance RL across which we are taking this output. So in that case, what you have seen, across this diode there will be a voltage drop of V gamma, right? So V output, if this is Vm sine of omega t, then we have seen the maximum V output, V out max, we get Vm minus V gamma. So there will be a drop of this V gamma. For silicon diode it is around 0.6 or 0.7 volt, right? But for this circuit, what you can see is that whatever is the input voltage, that will be the output voltage in the positive half cycle. That means the voltage drop across this diode when the diode is in forward bias is compensated by this op amp. Means the op amp will adjust its output voltage V, which is V naught 1, such that this V gamma part it can accommodate here, right? So that at this output voltage V output you get only the VI, right? So that means this particular circuit you can use as a half wave rectifier, and here the output is quite precise in terms of what is the input voltage, the same output voltage you are getting. So this type of half wave rectifier which has been implemented using this op amp is called precision half wave rectifier. Precision half wave rectifier. Fine. So then here if it is suppose silicon diode and it has a drop of around 0.6 volt, then if you want to apply a signal whose highest magnitude is 0.2 volt, that you cannot use here, right? For this normal for this normal half wave rectifier circuit. However, that 0.2 volt amplitude maximum amplitude signal you can use in this precision half wave rectifier to get the rectified output, right? Okay, so in that way, if you recall that for this rectifier we have actually drawn one characteristics which was like this. This is V output or basic, and this is V input. So basically V output is here, this V naught, that's what how we are representing here, and this is the input voltage, output versus input voltage for normal half wave rectifier. So here we have seen we have this drop of V gamma. After that V gamma, this output will increase as we increase this Vi, and here that slope was equal to 1, right? And this is for the, again remember, normal half wave rectifier, always we have a drop of this V gamma drop, and after that you get the rectification. Whereas for this precision half wave rectifier, if we plot this output voltage versus this input voltage, then we can see from the 0 voltage onwards only it will rise, with V output will be proportional to this V input. Here also this slope is equal to 1, right? So normal case you have below, if the below cut-in voltage you don't have any signal. Once the input voltage crosses the amplitude of this input voltage crosses the V gamma, then only you will start getting the output. But in precision rectifier from the 0 volt onwards only you start getting the output for the positive half cycle, right? So I hope then this precision half wave rectifier part is clear to you. Okay. In the next page, let us also discuss two more op amp circuits where we will also use this PN junction diode, but not in this fashion. In one case we will use the diode in the feedback loop, and in other case we will use the diode just before this non-inverting terminal of the op amp. Okay, and we will try to analyze what will be the relation between then the output voltage and the input voltage of these two new circuits. Fine. So first we will try to analyze one circuit where the diode is used in the feedback loop. So here this is the op amp whose non-inverting terminal is grounded. This is the output voltage is V0. This is the input, and with this input we have connected one resistor R, and here is the input voltage Vi, and as mentioned we will place one diode in the feedback loop, right? And let us say the current which is flowing through this R is I1 and the current which is flowing through this diode is I2, right? Okay, and as this is grounded, this terminal, right? And if this diode is on, right, then we have a feedback and the op amp is now operating in the closed loop condition. So we can also say that this potential is also equal to 0 considering the virtual ground concept, right? Okay, then how can we write I1 in terms of this Vi? It is quite straightforward. We can write I1 in terms of this Vi like this. What about this I2? So how can we write or express this current of a PN junction diode in terms of its voltage? We know the diode current voltage relationship, we can use that. So I2, if the voltage is here V, is nothing but IS. IS is the reverse saturation current of a PN junction diode into exponential of V by Vt. We are considering eta equal to 1, right? V by Vt minus 1, right? Fine. So let us keep this Is, right? And what is this V here? You see here, this is 0. So this is V naught. So this V is nothing but 0 minus V naught. So it is minus V naught. So it is minus V naught by Vt minus 1, right? This is I2. Now we have also discussed during our analysis of diode circuit that if this voltage drop across this diode is much greater than this Vt, right, then we can neglect this one term, right? So in that case we can write I2 is Is into exponential of minus V output by Vt, right? And from the circuit it is clear that I1 is equal to I2 because no current is going inside to this op amp, right? So as this I1 is equal to I2, then we can write Vi by R is equal to this V output by Vt, right? Then we need to express V output in terms of this V input, right? So let us do that. So it is V output by Vt will be equal to, or let us keep this negative sign also here. So right, so it is ln of Vi by Is into R, right? So then what is this V output? V output is minus Vt ln of Vi by Is into R, isn't it? So from this relation of this output voltage and the input voltage, you can clearly see the output voltage is proportional to the log of that of this input voltage, right? So this particular circuit, okay, is called log amplifier. Log amplifier. So is this log amplifier is clear to you? Okay. So in that case, okay, fine. So in that case, in the next page, let us try to interchange the position of this R and this diode, resistance and this diode. So here we are planning to interchange the position of diode and the resistor. And you remember this non-inverting terminal was grounded, so we'll keep it like that. Earlier at the input we have the resistor. Now we will place the diode in this input, and in the feedback path we will place the resistor. Right, this is R, this is the diode, this is the input voltage Vi, this is the output voltage V0. Right, so considering the virtual ground, this is again at zero potential, and if this current is I1 and the current flowing through this resistor R is I2, then this I1 can be expressed as Is exponential of Vi by Vt. Vt is the thermal voltage, right? And this minus 1 part was also there, Is into that minus 1. We can neglect it because we are considering that this Vi is much greater than this Vt. So this minus 1 part is been neglected, right? Okay. Now what is this output voltage? V output. So V output can be written in terms of this I2 and R like this, right? Okay. And we also know the I1 is equal to I2, same current. So V output can be written as Is exponential of Vi by Vt into R. This R is this part. This is I, this is R. So write it in a this way. We can write it like Vi by Vt. So here from this equation you can clearly see that the output voltage is related with the input voltage, right, when exponential fashion, or this output is proportional to the exponential of that of this input, right? So this type of amplifier, okay, is called anti-log or exponential amplifier. Anti-log or exponential amplifier. Anti-log or exponential. Fine. So I hope then if a op-amp circuit is given to you with resistor, capacitors or diodes as in peripheral components, right, then you should be able to find the relation between this output voltage and its input voltage, isn't it? Okay.